Okay, thanks for the wait, everyone. I think the time now is 6:35. So we'll begin our workshop today. So let me introduce our speaker today, Bebek, who is a senior data scientist at Chope. It's really an honor to have Bebek with us here. I will just go through an overview of the workshop for today. So for part one, we'll have some theory concepts being taught. Then after we will have a 5 minute short break. Then after we will move on to part two, which is the real world applications. Then at the last part, we will have a Q&A session. Then after Q&A, we will have a group photo. Then after it will be converted at the end of the workshop today. So now I will pass on the time to our speaker today, Vivek.
Yeah, hi all. So as Jack already introduced me, I'm currently working for Chope, but I have experience in retail companies like Alibaba and also a news company like MediaCorp. So my specialty is mostly recommendation, and currently I'm working in search as well. So let's start the presentation. Just I wanted to know what is the background of most of the people? Are they from computer science, or do they come from like different branches?
Yeah, please do not feel shy. Yeah, you can just type your answer in the chat box. Yeah.
Okay, we have maths people here and electrical engineering. Okay. So yeah, we seem to have like more or less maths background people. So in this presentation, we have some maths, but not very complex. But there will be some basic concepts from computer science. So I think most of our audience is aware of those concepts. So let me start with the presentation. Okay, so our content is very similar to what a data science problem looks like. It's a pipeline like intro and problem definition, some data collection, data processing, algorithms, and there are some larger problems which we deal in recommendation, and finally some metrics associated with recommendation. So I want to explain it through a flowchart. Think of it like data is coming to you. What do you do with it? So first of all, if there is data or not, if there is no data, for example, there is nothing to start with, and you want to build a recommendation system, you just have maybe set of products. And so you show them some welcome heuristics, like they come to the website and you show them like top products, or you sort them with some categories or some behavior. And the other way is, for example, if you have a news website, you can show them the trending news, like whatever is news is popular at this time. Without knowing any background about the user, you can simply start predicting. So what is the other scenario is that you have a lot of data. By data, we mean user-based data and product-based data. So recommendation is also based on that. So if there is a product information, then we have product-based recommendation. So what do you mean by product-based recommendation? Like similar products, bought this, bought that. I mean, like substitution products, viewed this, bought that. So these are like complementary products. Similarly, you have profile-based recommendation, like based on the behavior of the user on the website. So you have recently viewed, based on which you make a profile of the person, like whether he likes certain things, likes, dislikes, or you can make some personalized based recommendation, which is based on his behavior on the website. So let's go to so this is a very generic representation of recommendation. Let's deep dive into it. So what is the formal definition? So we basically want to find the utility of an item to a user. So we assume like we have a set of users, we have a set of items, and we show them in the rank of their utility. For example, if it is a movie, it could be like how likely is the person going to see that click that movie if we show him? Or if it is a news item, how likely is he going to read the news item? So this is more or less like probability, but yeah, it could be like more numerical also. I mean, binary, 1 or 0. So let's look at some of the recommendation algorithms. So recommendation is a very complex and has a lot of history. So there are a lot of algorithms associated with it. For example, like in the initial days when there was no like machine learning, they used rules. Then it became content-based methods where you just look at the content of the article or the movies or some products. Then you have collaborative filtering, which is like how you find the k nearest neighbors. So let's say you have some news article. What could be the likely other news articles? Then there is matrix factorization. So this is slightly where math starts to come into the picture, because this was like late 90s when maths had developed and matrix algorithms were popular. So they decided to use matrix factorization to recommendation. What is matrix factorization is basically a matrix. So the input to it is a matrix, which could be like the whether the person watched the movie or what rating he gave to the movie. Based on that, you can make a matrix. And that matrix, when you factorize it based on certain algorithms, you get vectors. So these vectors are like representation of the users or the items. And then you find how likely the user is going to click or buy that item. So that likeliness is based on the distance. So this is where maths comes in. Like, and after that, when we go to deep neural net, there is truly like very complex maths. So this can do a lot of things like predict rating. For example, if we don't know how likely the person is going to watch the movie, but we know some other people who liked that movie and gave certain ratings. So deep neural net can help us find these ratings. Other things could be like predict next user action. So for example, if he's going to buy the product, is he going to put it in the cart, or is he just going to click it? So this could be like, there could be n number of actions which could be predicted based on a like a finite state machine kind of scenario. And finally, there is user item attributes embedding. So these are coming from autoencoders. So these are like the advanced techniques, and we'll go through them in the sequence of how I presented here. So let me show you the overall picture. In the overall picture, what you see is like every segment has a lot of depth to it. So what is data collection? So you collect user information, you collect item information. That is the like very basic level. Then you go to the images, comments, catalogs, demographics based on the user's location or his age, gender, where does he live, what is his ethnicity, etc. Then you have his behavioral patterns like clicks, views, payments, cards. And finally, we come to how he interacts with the website, like the ratings he gives. And last of all, there are some product information like categories, subcategories. For example, if you are looking at food items, it could be a broader category could be Asian cuisine, but like a subcategory could be chicken biryani or like veg, non-veg, etc. So next thing is how do we process this data? So based on the information that we get, we cannot always use it directly. For example, if you want to use user information for matrix factorization, how do you use it? So for that, we do data processing, and for that, we calculate different kind of embeddings. So these embeddings are just like high dimension representation of users, items, images, documents, whatever format we are getting the inputs. And there could be some very complex data processing tools like knowledge graphs. So these knowledge graphs are like built on top of these structures called user items, images, documents, where we try to find patterns that combine together some of them and form like clusters that have some meaning. So let's come to the algorithms. We already discussed about them. The larger problems also we saw, like best or latest similar products, bought this, bought that, and then comes the evaluation. So this is like the horizontal and vertical of the problem. Let's look at some data collection. So if you look at movie ratings, how do the data looks like? So there are some movies which people have given rating, but there are lots of movies where they have no ratings. So imagine like this kind of scenario where Alice, Bob, Carol, and Dave, these are four people. And these are the five movies like Love at Last, Romance Forever, Cute Puppies, Non-Stop Car Chases, Swords versus Karate. So we have mixed here romantic movies and we have mixed some action movies. So the people who like romance may not like action, and like vice versa. Like so, as you can see, Alice and Bob, if you see, they have high affinity for romance movies. Similarly, Carol and Dave, you can see like they love action movies. So the embedding here that we get is x1, x2 are two dimensions. One is romance, one is action. And you can see like Love at Last and Romance Forever has almost romantic movie, Cute Puppies of Love also are action romance movies. On the other hand, Non-Stop Car Chases and Swords versus Karate are action movies. So if you use a matrix based algorithm like SVD, you will directly get these vectors. So this is how the data looks like for a matrix based algorithm. So some of the data types that we have, I think if you have some machine learning perspective, then you might be knowing like what is supervised and what is semi-supervised. So all our data in recommendation is mostly supervised, but some of them could be semi-supervised. For example, how do we infer the embeddings? So when we don't have enough information about them, like we saw, right, rating, there were some question marks. So not every data is labeled. So whatever is not labeled, we call it semi-supervised. So for supervised, we use logistic regression to predict the ratings or least square methods. For semi-supervised, we have embeddings, which we infer from the incomplete information. So by inference is like a very complex problem, which is like a proper mathematical background. So we need to go deeper into it to understand how we infer these embeddings. So the data sources, so for demographics, we have age, sex, location, education. There could be salary, there could be occupation, this kind of things. Shopping data is click, views, payments. Products, item information like which category they belong to and which country they are available in, what is the price, etc. Seller could be also having categories like what kind of seller is, what type is, like there could be some classification of sellers based on their performance and which kind of products they sell. So these are more or less the structured data that we have. What about the unstructured data? So structured data is just like 10-20% of the total data. But the unstructured data, which is like the real gold mine of this field, that comes from three different places. NLP, like all the text that we have. So it could be reviews, comments, catalogs, tweets. So catalogs are basically unstructured because you get them in the PDF format or in the image. So you have to convert it into a table, then it becomes structured. For vision, we have images, we have product pictures. We need to convert this into embedding, only then they will be useful. Or we need to do some kind of OCR to get the text out of that. And conceptual, like these are some fields which are above the field of NLP and vision. So this we make from the whatever data we have. For example, sentiments. So we just go through some text and we do sentiment analysis and we get whether it is positive or negative. We have satisfaction, which is very like vague conceptual topic. We have vulgarity, which is like whether the content is vulgar, has nudity or something like that. There are frauds, like some sellers who act to sell, but they are actually not selling anything, just trying to products which are clickbaits. So these things have very high, people view them a lot, but hardly they click it, or they even harder to buy them. So these are all the data sources that we have. And to get some data set, to get the real examples, we can go to Netflix price data set, which is 100 million movie ratings, and then Amazon reviews, which is 233 million reviews. So yeah, if you have any interest, you can figure it out from the internet. I think they will be available. Let's go into data processing. So why do I need to do data processing? The first reason is sparsity. So any retail data, if you see, a lot of the products or user table will have empty columns. And secondly, you have a lot of items which are newly added. So you don't have any information about them, and new users, like people who just come to the website. So you can just treat them as random algorithm, or there could be like some heuristics based algorithm that you can deal with. So that is the reason for data process. That's why we need to get like automatically detect which place they are coming from, what is their IP, what location they belong to, and what kind of phones they are using. So that's where we need to do data processing. Other reason for data processing is it's a huge data. For example, if you just look at clicks, it will be in the millions, in the terabytes. And you cannot use so much data in the format it arrives in. So you have to convert it into a format that could be processed by a standard GPU or something like that. So if you just look at images, it could be in the billions, in TBs easily. So how do you convert? First of all, you need to convert it into embeddings, and then only you can use them. Similarly for reviews, like if you just go through the text of the reviews, it could take you years just to like tag them with sentiments. So we need some unsupervised way to get sentiments, satisfaction, etc. And lastly, like there are a lot of hidden data. For example, clickbait. How can you figure out whether item is clickbait or not? How do you know whether image is vulgar? So for this kind of information. Yeah. So let's go to the next part. So let's look at one of the interesting features, which is called OneHot Encoding. So see, basically, like if we have a lot of classes within the same feature, for example, movie, it could be actor, director, genre. So these could be some of the features name. Genre is a limited set, like it could be action, romance, comedy. So what you do is you take this vector, but you convert it into a OneHot encoding. So whenever let's say the index of the position of the vector, it gives you the genre. So if it is position one, let's say it is comedy and then romance, and we create a OneHot vector for it. So a movie can fall into both comedy and action. So here, what example you see is like A2 and A4 is blue or highlighted. So it means it belongs to two genres. Similarly, we have another feature called embeddings. So these are based on movie reviews. Sometimes we can get text embeddings, or you can just imagine whatever data we have, we are just trying to compress them into some high dimensional feature vector, and then we can mathematically manipulate them. And the good thing about embedding is they are very dense in nature. So the sparsity problem is resolved in embeddings. So let's see some examples, like how can we get embeddings. So if you have a text, one way you could do is count the number of words in the document, and then you can create a feature vector from that. So just if you count it, like let's say the appears like 100 times in the document. So that's not a good number, because ultimately these numbers will decide which category the document belongs to. So what we do is rather we just don't take the count of the word, but we also see how many times it appears in all the documents. So if it appears in all the documents, then it is the least important one. So we take an inverse ratio of that. So as you can see, what TF-IDF does is, in the first place, it counts the word. In the second place, it counts how many times it appears in all documents and takes the log of that. So basically, if the documents appear in all, the word appears in all document, this will basically become 0 and its weight will become 0. So, and if it just occurred in one document, then its weight is the maximum. Yeah. So next concept is like, these are basically based on frequency. So they are useful up to some extent. The fact that we just use frequency, we don't have any other information. So how about we get some more information, like what does words actually mean? Like, is there a pattern why we see some words in between some other words? Or when we see a sentence, is there a pattern in that? So these are explored by two basic algorithms. I mean, now it is basic, but a couple of years back, it was like a big innovation. So the first one is word to vec, which is basically what it means. Every word you convert into a vector. So in that, we have two different algorithms, SkipGram and CBOW. So I will explain what these two are. And the second one is a transformer. So transformer was like an advanced version of word to vec, and it was developed by Google. So let's look at CBOW and SkipGram. So CBOW is basically contextual bag of words. So what you're trying to do is, if you have the sentence, I'm visiting the park today, and you don't know this word visiting. So how likely is that this word is visiting? So you try to predict every word given its context. And the other algorithm is SkipGram. In this, only if you know visiting, can you predict its neighbors. So this is the difference. Like, conceptually, they are almost, they try to find out the same thing, like the meaning of the word, but their approach is very different. One tries to predict a given word given the context. So context is very important. And the other one tries to predict the context given the word. So in this way, they are like diametrically opposite. And let's look at what is a transformer. So as you know, like, transformers have started existing since, I think, 2016-17 onwards. So very popular one is BERT, and it has been followed up by some variations, which is called Roberta, Albert, something like that. And the basic mechanism which is behind this is the attention mechanism. So this attention mechanism, it learns the contextual relation between words. So what do you mean by contextual relation? Like, it could mean a lot of things, like how far they are from each other, what is the pattern behind them, how frequently they occur, and most importantly, like, what do they mean to each other? Like, how important is word one in association with word two? For example, I'm going to the bank to get some money. Here, bank and money can have high importance with each other. So this attention mechanism tells us this importance matrix. So here, money will tell us that this bank is a financial institution and not a part of the river. So that is the difference. Like, uh, compared with frequency based algorithms, these algorithms have a lot more information. So the direct output of these algorithms are to generate a language model. So if you have done Google search, you would have seen like predict the next word. This comes directly from the language model. So when you write a one word, it starts predicting the next 2-3 words. So how does it do it? It pre-builds these models. So it pre-builds like what could be the next word, and then the next word, and then the next word, and so on and so forth. And it also adds your personalized attributes to it, so as to know like what you are most likely to search compared to the rest of the people. So how does this embedding is created? So a sentence pair is given as input, and some of the words are masked. So these masked words your model needs to predict. This is very similar to like CBOW, but here more than one words can be masked. And these masked words don't have any pattern. They can be randomly assigned in the text. So when you finally predict them, you check them with the correct answer. And if it is incorrect, you try to modify your deep neural net. So this is a transformer landscape. If you'd be interested in some history, like BERT was the first one, which was developed by Google. And then OpenAI came and they had two models, GPT and GPT-2. After that, Transformer XL came, which was an English model trained on Wikitext, and then XLNet, and finally XLM, which is trained on 100 languages. So XLM is one of the most complete language models that we have right now. But for practical purpose, we use XLNet. Similarly, the same thing has happened in the field of images. Currently, the image world has the maximum usage of embeddings because they have an algorithm called CNN, which is a convolution neural net. So basically what it does, it finds structures in images. So in images, the structures are very important. Like, do you have any object over there, or you have any humans, any important information which you can parse from there. Similar to CNN is VAE, which is a variational autoencoder. So if you give an image to this, it will convert it into one-dimensional vector. And it's a lossless transformation. So there is no information loss. And it is based on the encoder-decoder architecture. So what do you mean by encoder-decoder? So first step is an encoder deep net. So what it does, it takes the image and converts it into a low dimensional vector, like let's say 10 dimension or 20 dimension. So you try to compress this entire image into this much information. Then you try to recreate that using a decoder. So decoder will try to do the reverse of what the encoder did and try to recreate the image. If you are successful in creating that image, that means you have obtained like a stable state for the neural net. Then comes ResNet. So ResNet is basically a large-scale deep learning model used for image similarity and classification. And finally, there is EfficientNet, which is like a class of automatically generated models. So ResNet is the one which is very popular for any kind of image tasks. Okay, let's look at some of the deep learning frameworks. I mean, we'll see them in two axes. So bottom one is million number of parameters. Like basically it means how big the neural net is. And the upper one is intelligent top one accuracy. So these basically have been evaluated in number of tasks, and based on that, this ranking has been done. So if you see like there are three lines. The first line is the red one is basically how the efficient net parameters, I mean, how its accuracy changes with the number of parameters. And that's the reason it is called efficient net, because it reaches high accuracy with very low number of parameters. On the other hand, algorithms like NASNet or AmoebaNet or Inception, these take comparably longer time to reach that same accuracy. But even then, they won't reach to that higher level. So let's go to some of the algorithms, like how we actually figure out these ratings when we have incomplete data. So what the problem in hand is predicting the movie ratings. So as you can see here, there are some question marks and we need to predict them. And what we have are these information, which is basically like their importance to certain features like romance, action, etc. So how do we do that? So we start with like a very simple vector. Let's say a feature vector we have x in 3 dimensions, and we have a user vector which is theta, and it is 0, 5, 0. So when we try to predict how accurate they are, we get that this user, this this particular movie or this thing has a central rating of 5, and this user has a preference of 0.99 for that central feature. So it will be rated 4.9 in that case. So this is basically how we predict all these values. So we take these 3-dimension vectors. So we convert Alice into a 3-dimensional vector. Then we convert x1, x2 into 3-dimensional vector. And then we get these ratings. So problem formulation is quite complex, like it looks very mathematical, but if you look at the text, so you basically try to rate every movie first using 1 and 0. Then you give a rating, which is whether it is between 0 to 5, and then a parameter vector. So this is the basically the hidden thing that we are trying to estimate. A feature vector, which is based on user's preference. And for user J movie I, we have a rating formula, which is basically a product of the parameter vector and the feature vector. And you have a total number of movies, that is MJ. And J here means a number of movies rated by user J. So this is a optimization objective. So I won't go like very deep into this, but what it means, like when you're trying to estimate the rating, you try to get a difference of the predicted rating and the real rating and square it, because you don't want negative values to cancel out the positive values. And then you try to balance out those weightage given to the parameters. So if you see this part of the equation, this tries to balance out the weights, and this part, it calculates the accuracy loss. And there is a learning algorithm which shows you, which basically tells you how to update your theta values. So how do you update these parameters every iteration? And the overall like objective of this is to minimize this thing, this entire J. It is called the cost function. So our objective is to do a minimization of that. And how do we approach this problem? We use gradient descent. So what gradient descent basically does is, imagine that there is a curve. So let me like go to the whiteboard. Okay, I'm not able to find the whiteboard. Okay, let me just stop sharing. So let's think like you have a curve like this. This is your utility function basically. And this is your some dimension in theta. So in that dimension of theta, you are trying to reduce the utility dimension, utility value. So what you want to do is you want to go down this slope. So what do? Suppose you are at this point, you measure what the slope is. So this slope is negative. So to make it move along that direction, you just need to subtract that value. So if you subtract it, the theta value will increase and it will go here. And it like that, you try to come here. But when you are here at this position, you might jump over to here, because it depends on how much you want, how much you're estimating your right value to be. So if you go here and you still keep on increasing, you will go up the curve and you'll never reach the optimum point. So here, if you measure the slope, this is positive. So when you subtract this slope, it comes back in this direction. So that is the logic. Like this is called gradient descent. And as the name suggests, you calculate gradient and you descend in that direction. So let's go back to our original. So are you able to see the screen?
Yes, we are able to see the screen. I think there's one question from the audience.
Okay.
From Brian. He's trying to ask, what's the superscript T behind the theta? What does it mean?
Theta is basically transpose. So when you're using two vectors, you cannot take the product directly. So you just take a transpose.
Yeah, I hope that answers the question for Brian.
Yeah. Then let's go back to
yeah.
Oh, I'm sorry. I think I just Okay, so that is our gradient descent update. So here you can see they try to update these theta parameters using this equation. So it's a pretty complex algorithm. Let's not go into that. So yeah, so based on these, so in the previous problem, we had assumed like some values for x1, x2 to be like 0.9. But how do you measure them directly from the data without assuming any values? How do you get the exact values in fact? So there comes some other algorithms called collaborative algorithms. So what are these algorithms basically? So these are where we try to learn the feature automatically without taking any iteration or anything. So what do we have in this case? We don't have any information about movies, like we don't have that theta parameters, but we have information about user preferences, like what do they like. So let's go to some optimization algorithm again. As in this case, you can see similar sort of setting where you have some theta and you're trying to learn basically x here. So you're trying to minimize that loss and you have these given conditions. So what does collaborative rating is collaborative filtering? How does it work? So you have been given all these feature vectors, like what does the user preference is and movie ratings. Now you have to estimate the theta. So, and given theta, you can estimate back the x. So that is the logic. Like if you know theta, you can of course estimate what is their preference because you can take a dot product. So how does it work? Like, can you start making a guess of a theta and then you get an x and then you again get theta from that x and keep on doing this until you reach convergence. So this is called collaborative filtering. The collaboration, because different users are collaborating to determine the movie ratings of each other. So, and it's not about just movie ratings, it's also about predicting features. And because of that, we get good features and they can help us make better predictions. So let's look at the optimization objective here. So what is the difference here? So there, if you see, you have been given this and you have to learn theta. So you're trying to vary this theta and trying to minimize. So this part is more or less the same thing. Given theta, then you try to learn x1. So here is where the difference comes. So you not only change theta, but you also change x. So you have two directions to think about. How do you optimize theta? How do you optimize x? And then you have a joint objective. So what does the joint objective mean? Where you try to combine the losses of both. When you have some theta, you get x. When you have some x, you get theta. So now you not only have to look at the loss function, but you also have to check whether theta and x are well balanced. So this is called a joint joint utility function, J, which takes all x and all theta into equation. While in the previous case, if you see, in the previous case, you just have theta as the varying thing. You're just taking updates for theta, not for x. So how do you start? You basically have very small values, small random values, because you don't want it to increase like to a massive value. Then you try to minimize the j using gradient descent. Example is like this, how you update those values. It is very similar to what we saw in the previous slide. So now for a user with parameter theta and a movie with features x, you try to predict a rating of theta transpose x. So this rating will give you some value between 0 and 5. And based on that, you can reevaluate theta and x. So that's why the collaborative word, because you take both theta and x together. Now let's look at some of the larger problems that we have, as I saw and showed you in the previous slides. So best or latest? So this is the one most common thing we see in movie website, like sort items or movies based on some criteria. For example, if we try to buy something from a website, we always sort it by price. So this comes from recommendation. Similar products. So if you are buying something, what is some other product that you can also buy? So these are basically, if you have vectors from them, you can just imagine like closure vectors. Bought this, bought that. So these products are not very close to each other in the vector space, but they are very close in the complementary space. So imagine you have a complementary space along with this similar product space. So in the complementary space, they are not, the items are never together which are similar. The items which are complementary are closer to each other. Then there is recently viewed, for example, sort items based on history. This is very common one for like food ordering things. So some food which you have ordered in the last couple of days, you might be more likely to order it again. And finally, there can be something like more, this is not directly used by the person, like predict rating, but this gives the website a idea like what he may be likely to buy, or predict next user action. So for example, in case of a time series problem, you can compute some reward or utility based on user action. So if user takes this action, he gets this utility. And based on that, you can do some marketing based on that. So this could help us in marketing. And lastly is a cold start problem. So this is a very common problem when you have problem with initialization. Like there is some movie which has no information, some user who is new to the website. Okay, so this is again a recap of the algorithms. So far we have done content-based collaborative. Now we'll go towards matrix factorization. Oh, okay. So maybe I don't have slides, but basically probably they're very advanced or something, but I will try to bring some other topics. Let's look at evaluations. So when you do all these classification or clustering problems, you always have some metrics associated with it. Like for image or text, if you're doing classification, you can use recall precision. So what is a recall? So you're trying to show some documents to a user, but he clicks only certain of them. So those items which he clicked could be coming from your gold document set, or it could be coming from the set of documents that you have. So when you're able to get a large number of documents from your gold document set, it is called as better recall, because whatever you give to the user clicks. But if you give some items from your other document set and still the user clicks, then you have a high precision, because what you are suggesting may not be from his past history, but still he's clicking on that. So both of these metrics are very important. So you should not only show what he has seen already, but you should also show him something new which he may click. And together, when we combine them, recall and precision, it is called F1 score. So this F1 score is a good indicator that your overall algorithm is complete. Then you have on top of that AUC and MAP. So these are like slightly advanced version of these metrics. So AUC is basically area under the curve. So this is based on the concept of threshold. So when you're trying to classify some image, some text, you have a threshold beyond which you will classify as something as 1, and below which you will classify something as 0. So if your threshold is varying, how does it affect your accuracy? So if your threshold is, let's say, 0.75, so if you think that 75% of the time the person is going to click the movie, and you show him the movie and he clicks on it, it is good. But if you think like only 30% of the time he's going to click the movie and you don't show him, but actually he clicks it, so that's a bad thing. So that's what you try to plot in a curve. And the area under this curve actually gives you accuracy over all these threshold ranges. So the higher the AUC, it is better. Then we have clustering problems. So clustering problems basically are unsupervised problems. So let's say you have some data about some users and you try to cluster them so that you can do some sort of marketing. For example, how many of your users would like television, for example? And you cluster them into two groups. Like group one has high affinity to buy television, group two has lesser affinity. So how do you determine, like, in this case we have two clusters, but it could be a generic problem where we might have multiple clusters. So how do you find the number of clusters in that case? So since you don't have any metrics, you use something called as elbow method. So in this elbow method, you try to vary the number of clusters and see how it improves your accuracy. At certain point, the accuracy will be maximum. So increasing the clusters beyond that will not help, and decreasing the clusters below that will make it less accurate. So that's why it is called an elbow method. And there are some other ways to also understand the clustering problems. Like let's say you get vectors. How do you know whether they form good clusters or not? So what you do is you try to convert it into a lower dimension and try to visualize them. So for visualization, a very good algorithm is TSNE. So TSNE basically converts a high dimensional vector space to a low dimensional vector space. And then it also has some, basically it can still have the relationships that was there in the higher dimension. So imagine like the things which were close together in the higher dimension are still closer together in the lower dimension. So you preserve the distance. And when you can visualize the higher dimension objects in lower dimension and you see clusters, you know that your clustering algorithm is actually working. And finally, there is a regression problem. So what is a regression? It is basically you are trying to predict something which is numerical. For example, it could be something related to like house prices or like ratings of a movie. And there is a very important problem here, which is called CTR CVR. If you know, it is called click-through rate and conversion rate. So when you try to predict CTR, you try to predict whether a document will have high CTR or not, like high click-through rate. So most of the users, they come and they try to click it or not. And similarly, you have a conversion rate. So in conversion, it's mostly related to whether the product is bought or not. So if a product is clicked, but it is not bought, that means it was not converted. While if it was bought, it is converted. So we try to predict these things also so that we can recommend these items. And the metrics that we use is RMSE, which is a root mean square error. And this basically gives us an idea like how accurate our algorithm is. So this is the end of part one. I don't know what's the time right now.
Okay, thank you, Vivek. So I think the time now is 7:23. So
Okay.
for now, we'll have a short 5-minute break. So we can come back at 7:29 maybe. Okay.
Okay. Okay.
And
Fine.
if the participants are having any question to the first part of the presentation, you can always open your mic or type in the chat box to ask Vivek to clarify your thoughts.
Sure.
Yeah. If not, we can just come back at 7:29. Okay.
So I'll be back in a while.
7:29. Yeah, about 7:30 like that. Yeah.
Okay. Fine.
Okay, hello everyone. I think it's about 7:30. Okay, I think can continue with our part 2 of our workshop. Back, are you back? Okay, I think our speaker okay, oh nice. Just yeah, I will
I'm
stop
back.
sharing. Okay, I will stop sharing the slide for now. Then I think you can continue with part 2.
Okay, so this part I'll mostly be whiteboarding. So let me just clear this. So we'll basically design a recommendation system here. So let's start with something. Okay. So first, what we need to do in a recommendation system is to start indexing our documents. So imagine this, you're building it for a company. How will you do it? So first step is index documents. And okay. So by indexing, I mean I save those feature vectors for every document onto a server. So very popular server for this is Phase, which is designed by Facebook. So what this Phase does, it not only creates the index, but you can basically search every document by its embedding. So you can search it by ID or search it by embedding. And also you can get the k nearest neighbors. Like if you want to find the recommendation for a document, it will give you top 10, top 6, whatever you need. So output of Phase top k document. So once you have the system in place, like you can access a document through its embedding and you can get the top k results, you have built a sort of collaborative recommendation system. But this is a very like naive way of thinking where everything is based on the content of the document. So because the feature vector was based on the content. So this is what I call a content based recommendation. But this could be like a starting place. And one advantage of using it is it doesn't have any cold start issues because every document you can get the vectors. So let's say you have documents in multiple languages, then you can use a universal language model or a universal transformer in that case to get vectors in different languages. So So this is your basic model. Now you try to build something more complex based on the behavior. So let's assume your user is a person who come to the website and he visits some news website and he clicks on another website. So first he goes to like, let's say he goes to A. Oh, better to do it using text. He goes to A and how about Then he goes to B. Then he goes to C. And then he goes to D. Similarly, you have another user who comes to your website. He first goes to B. Then he goes to, let's say, E. And then he goes to F. And similarly, you have, let's say, another user who goes to F. He goes to C. He goes to A. So what do you see in these sequences? The sequences are basically creating a graph underlying this. So this graph is called a behavioral graph. So if I can draw it, it will look like a graph. But the thing is, like, we can get a very large graph, a very dense structure from every website that we build. And this graph tells us how likely is, let's say, user going to take a particular path. This path is important because there could be infinite number of paths in a graph. And to estimate all the paths, it will take us like a very complex algorithm. So we'll not go in that route. What we'll rather do is we'll try to find out random paths which a user might trace. And based on those random paths, we can generate a word to vec, like a embedding based algorithm, which will create these embeddings from these paths. So these embeddings can form the basis of your collaborative filtering recommendation. So you have another model here, collaborative. So how do you train these models? So these models are trained offline manner. So you cannot train it when the user comes to the website. You already seen his last couple of weeks data and you know what he's planning to do or what he's most likely to watch. So you build these models in an offline manner. So here you do some offline training. And in the offline training process, you have multiple algorithms. So let's say I have algorithm 1 and I have 2, I have 3. So what I do is I put all these models in one place. Let me call that as a server, which is a recommendation server. Or I can call it a deep learning server. So whenever these models are updated, their latest version will be informed to this server. So the server can fetch in real time those latest models. And when you try to access these models, you will get the latest trained batch. So now what you do is you create another server, which is where all your users will come. So let me call it the recommendation main server. So this is where all the requests come directly. Like when a user come to the website, he clicks, he sees your recommendation area, then that recommendation part of the website will send a request to this server. So what you will get is a request. So this request, you basically forward it to the recommendation main server. Now the recommendation main will ask the deep learning server. If the deep learning server has that user or has that content ID, for example, if it is a news item, it will have an ID, then it will fetch the results from there and show it to the user. So this is the case when everything is available, data is available. But what if the user is not available, or the user's information is not there, or we have no information about the content because nobody has seen it so far? So what we have is only the content information. Like let's say it's a news article. We'll have the news body, and we would have created already an embedding in the face server. So we'll approach the face server in that case. So face will return us the recommendations. So this is how you avoid the cold start problem. So this in this part of the algorithm is where you do all the cool stuff like training offline, building all the complex models, and then you upload those models to a deep learning server. Now this deep learning server keeps waiting on when it gets some request from the main recommendation server, and then it responds it. But the deep learning server always faces the cold start problem. To avoid that cold start problem, we have this phase server. The advantage of using phase is it is really fast. So it can index a millions of documents, and it can also calculate the neighbors very quickly. So how do you index these documents into the phase server? That is the question. So here uh, you have another server that basically does the job of indexing. So how do we start it? We have this encoder. So this encoder is a universal encoder. It will take all the documents. So let's say we have a document here, doc1, and in the output, we'll get a vector. This vector, so this document, let's say, keeps on changing. So we have to update that vector also. So every time a new document is uploaded, it immediately gets the encoded, and the vector is indexed in phase after that. And this happens very frequently, like every 2 minutes, this should happen. So this way you could index possibly a million sort of documents, and you can this system will never fail because it doesn't suffer from cold start, and you can build as many offline algorithms as you want. So there could be a set of data scientists who are training this offline system. There could be some DevOps engineer who is handling this main server and the deep learning server. And there could be some data engineers who are creating these documents. So this is like a full description of how a large scale like setup can work. So yeah, we can have any questions here.
Okay, so far, does anyone have any question regarding the recommend system? No? Okay, I think that's great. Everyone can keep up so far. Yeah, I think maybe I can continue.
Okay, so let me like stop sharing here. I'll go to the another like slightly fun problem to do. So I have a game to understand the collaborative algorithm, and I just want to play with people like how they understand it or not. So I will show you an example, like how very easily you can think of imagine this system. So you have some pictures here. Let's say this is like Amazon or something, and you want to buy some items. So this is the user one. He likes this. He likes this book, but he doesn't like this play button or YouTube or whatever it is. Then there is another user. He likes this image. He likes the book. Doesn't like the gaming console. Doesn't like the play button. Then there is this user who is slightly different. He likes this play button as well as the gaming console, but he doesn't like books. And there is a further another person who likes the image, who likes the book, but he doesn't like the gaming console. And finally, there is another, he likes the picture, but he doesn't like the book. So we have all kind of people who could be representative of our demographics. So what do you think? Should we suggest this play button to this guy? Because so far he has not seen it. So let's look at this puzzle. It's kind of a puzzle. So we have just noted down whatever observation we got. So finally, we come to the fifth person and we are trying to suggest him the play button. So what do you think? Will you like it or not? You can give your answers.
Yeah, I guess everyone don't be shy. You can just put your emoji, use the reaction emoji, or you can just type in the chat box also again.
Okay,
Yeah.
so Catherine said no. Ardi also said no. I think people understand how it works. Okay, so let me give you the explanation. So as you can see, this guy is very most similar to these two person. Like if you compare the matches he has, so with this person, he matches in this books and in the console. And with this person, he matches with the picture and the book. So both of them say no to this console. So this is how collaborative system basically works. It's an aggregator of information. That's all. So as was rightly predicted by both Catherine and RD, I think the answer is that. So yeah, so that's all from me. I think if you have any questions, I'd like to open up.
Okay, next topic. So I think that's all for the second part of the workshop. So for now, we'll move on to our Q&A session. Does anyone have any question regarding maybe Vivek's career of being a data scientist, or you want any advice from Vivek regarding data science or recommended system? Feel free to open your mic and ask him, or you can type your question in the chat box also.
Hi, Vivek. Yeah, my name is Chokka. So thanks for today's session. Like it was pretty insightful on how a recommendation engine works. So thank you. So the question I have is, if I want to work as an engineer who builds this recommendation engine, right? So like, what qualifications must I have? Must I have taken like certain modules, or like what must my portfolio consist of to enter this role?
So are you looking at it as a data engineer or as a data scientist?
Probably a data engineer.
Okay, then you need to have like a computer science background, and you need to do some data related courses like data analysis or uh, I think basic engineering concepts related to computer science, like OS
Okay.
and Linux. And if you are slightly advanced, then you can go towards Spark or Scala. I
Okay.
think that will be helpful.
Okay. Okay. Thank you.
I think IMAX is asking to go through the recommender system first. I think, okay, I don't know if we still have the board. Do you mean this one or the slides? Okay, fine. Okay. So what we see here is basically a combination of two models that we discussed so far. So on the left, you can see is a content-based recommendation. So what do you mean by a content-based recommendation? Is it is purely based on the content of the article or the movie or whatever it is. So how do you start with it? You start indexing all the documents you have. So you have the documents, you have the vectors, which is given by the encoder. So this encoder runs on a hourly or a daily basis once. It creates all the vector and then it pushes it to a server called Phase. Phase is basically a very large scale uh, document indexer, and it also calculates the nearest neighbors. So all the uh, basically top K documents you can fetch from Phase. So this is the base. This is the starting point of your building the recommendation system. Now this system is not very complex because all you need to do is create the vectors from a content. But what about the behavioral pattern of the users? So once more people start coming into your website, you get more information about the user behavior. Like let's look at some users. So these are three users coming to the website and they have a pattern. Like the first user, he visits A, then he visits B, C, D. Then there comes another user. He straight away comes to B, then he goes to E, then he goes to F. And similarly, there will be a lot of users who have a pattern of their visits. So when you figure out there is an internal hidden graph here. So this graph is called the click graph. So the way they move through the website, like from one content to another, gives us some insight, like what are the most frequent patterns that people tend to do or create. So this is why it is called collaborative based recommendation, because it is not based on one user or one content. It is based on the whole set of users you have. So when you have this huge graph, you can create random paths in it. And in that way, you can have a lot of training data. So maybe you only have like 10,000 real paths, but from those 10,000 real paths, you can create a 50,000 random paths. Now these random paths, you can feed to an algorithm. This algorithm has the ability to get vectors from these graphs. So how it does it is slightly complex and is out of scope. But imagine like if I give you a graph and you get the vectors. So there could be different algorithms to do it. What to vec is one of them, which we already discussed. There is another one, which is a matrix based algorithm and is called NMF, which is a non-negative matrix factorization. So I have used this in industry and it works quite well. And what to vec was used by Alibaba in the Double 11 sale. So both the algorithms are pretty like industrially scalable. And that's the reason we can use it for such large documents. So once you have these kind of graphs and the vectors, sophisticated vectors, I would say, you can basically have a set of algorithms running offline. So keep on training them. Like you set a schedule for each of these algorithms, half an hour, 1 hour, whatever time it might have. And then you basically cache these algorithms. By caching, I mean you save these algorithms to the server. So when the server doesn't have to load them at runtime, it will basically have a copy of the model. So how do you cache it? You basically, whenever you have trained a model, you deploy it directly to the deep learning server. And the deep learning server knows its location in some blob. Like if you know about clouds, you can save this model in blobs. So you can fetch that blob and you can load it, keep it loaded in the server. So now when a user comes to your website, if he is on some page, you know the content of that page, but you don't want to give like some content based recommendation because it would be very naive. So you will ask the deep learning server first. The deep learning server will use the best model. So we have A1, A2, A3. It will see which one is the most accurate one. And then it will recommend the most accurate model and give it back to the recommendation. And the recommendation will show it in the website. But in case that item has no history, so you don't have any graph for that item or any random paths associated with it. So then you approach phase. So what phase will do is purely based on content, it will give a recommendation. So this is the overview.
Okay, thank you very much, Vivek. Does anyone else have any more questions? If not, we'll just proceed with our group photo section.
Okay.
Okay, can we get all the participants to just on your camera if you're comfortable? Then we can take a group photo together. Yeah. Guys, please don't feel shy. So just on your camera for a few seconds after we take a group photo, then we're done. Okay, thank you, Max, Yoka, Catherine, Donovan, Ting, Anthony. Yeah, please do not feel shy. Okay, okay, nice. So I think we'll just go over this. So 3, 2, 1, smile. All right, thank you, everyone. Okay, so just a bit of promotion towards the end of today's workshop. So if you want to get a further update on TGIFHacks workshops for the next semester, you can just always follow our Telegram page, or you can also follow us on our Instagram also. Yeah, and I think Vivek, do you want to share your LinkedIn page so that you want to connect if they want to connect with you or contact you?
Yeah, sure.
Yeah. Yep. So for those of you who wants to connect with Vivek on LinkedIn, please use the link in the chat box. If not, I think that's the end for today's workshop. Thank you everyone for attending, and hopefully we can see you next time for the next workshop. Okay, thanks, Vivek.
Thank you.
Thank you, everyone. I think that's all for today. Bye bye.
Bye-bye.
Thank you.